Okay, so I think that we can already start. Well, welcome everyone to this new session of the Simna Seminar course. Today we're pleased to have with us Matteo Giacomini, who is a lecturer, Sarah Hunter lecturer, and computational engineering at UPC, from very recent actually. And he's also a postdoctoral researcher at Simne, working in the group of innovative algorithms for fast, accurate computing from the Severo Ochoa program. And today he's going to present us latest research on the from low to high order discretisations in surrogate models for parametric CFD problems. So, Matteo, when you want to start.
Okay, thank you, Nancy. Good morning, everybody. First of all, I want to thank the organizers for the invitation and also for the patience in rescheduling the seminar, which was originally due in December, but I had some issues and I had to reschedule. So you had to wait several months. So thanks for the patience and for being here. So as Ignacy, first of all, can you all see my screen and hear me well? Just to be sure that I'm not talking to myself. Okay,
everything is right.
So as Ignacy mentioned, this work is about low and high order discretization methods in utilizing the construction of surrogate models for parametric CFD problems. So first of all, let me acknowledge my co-workers, Antonio Huerta from UPC Simne, Ruben Sevilla from Swansea University, and Karsten Ottmer from Volkswagen Corporate Research. And of course, the invaluable contribution of my former PhD students who did all the implementation, or most of the implementation that you will see today, Vasilis Theolakis, Jordi Villa-Perez, and Luca Borchini. Now, as the title suggests, this talk will be mainly related to parametric problems and how to solve them. And this work starts actually from a problem that was brought to us by our collaborator, Karsten Ottmer from Volkswagen Corporate Research, which was the bottleneck that they're facing in Volkswagen for the simulation of flow problems with varying geometries. And this is just a sketch of the pipeline that we need to follow. For a geometrical model, this model needs to be meshed. So the first step is mesh generation. Then, of course, there's the CFD simulation and evaluation of quantities of interest for the problem under analysis. And once this is done, there's an update of the design variables, and we go back to the first step. So we need to change our geometry, remesh it, and recompute. Of course, this is extremely computationally expensive and inefficient, especially for this second step, because as I'm sure you all know, the mesh generation part when complex geometries are involved is actually the bottleneck of most industrial applications. They take up to 90% of the whole pipeline time, according to our industrial partners. So the first bottleneck which was identified was the necessity to correct the CAD geometry and the necessity to work around the fact that we need to correct the CAD geometry and generate a new mesh which is suitable for computation at each iteration of this optimization algorithm. So the first question that I'm going to try to answer today is, how can we efficiently test a large number of configurations? This is true for geometry, but this is also true for other kinds of parameters, other kinds of problems. This is, for example, a parametric study that we performed during the thesis of Vasilis in the context of flow problem. This is a geometry go back to this example actually later on in the talk, but this is a geometry that was provided to us in Volkswagen. There's here a jet that is applied on this pipe, and these are different configurations that are computed either with suction or with blowing jets, and the goal is to reduce the recirculation effects that happens near this band. Of course, the simulation of this flow control problem leads us to another bottleneck, which is the necessity to compute multiple queries of the same problem using different parametric settings. And of course, if we want this kind of control and optimization problems to be done interactively, the critical aspect is answering the question of how can we evaluate several different scenarios in real time. And with these two questions in mind, let me introduce a bit the mathematical framework that I'm going to work with. I tried to minimize the number of equations in my presentation, although I'm a mathematician and I have the tendency of filling up equations. So bear with me with the few equations that I put in. And the mathematical framework is the one of parameterized PDEs. And how can we compute efficiently the solution of parameterized PDEs? And the answer that I will try to convince of is through computational vademecums, and specifically the proper generalized decomposition reduced order models. So let me briefly introduce this model problem. This is a parameterized PDE, the classical heat equation, the Poisson equation that we have here. It's set in a domain omega, which is open-bounded. It has NSD dimension. And moreover, there's a set of NPA parameters which may describe the geometry of our domain, the physical properties like the conductivity, the boundary condition, the source term, whatsoever. So what we have here is actually a solution U, which depends both on space, the spatial variable x, and the parametric variable mu. So we are seeking a solution for this problem, which actually lives in a higher dimensional space, which is a subspace of RNSD plus NPA. Just to give you a quick example, the case of two parameters in a three-dimensional setting, we are working with a PDE which is in dimension 5. Why so? Well, basically because the parameters mu are considered as extra coordinates of our high-dimensional PDE. And then we need to solve somehow this equation. Imagine that we work with finite elements, so we can write down our weak form of the problem, where our solution U will be living in appropriate functional spaces. I don't want to go into the details, but basically you can imagine that this calligraphic V is the classical space where you seek the solution of your Poisson equation, so a subspace of H1 of omega, and this is the traditional square integrable space L2 for the parameters. And our variational form at the very end of the day is a bilinear form capital A equal to a linear form capital L, and which have this expression. So just bear with me for a second, forgetting about these two integrals and focusing on this small a over here. Small a over here, if you have a look closely, is the classical term which comes from integration by parts of our heat equation. So it's a bilinear form, which all the properties that this leads, cursivity, continuity, and so on and so forth. And this is the linear form which accounts for the source term and the Neumann boundary conditions. Of course, since now the data of our problem and the source term, the boundary condition, may depend on parameters. Here, by the way, I'm assuming that the domain is fixed, okay? Since all this data may depend on parameters, this bilinear form and this linear form themselves, they will depend on parameters. And this is why this mu appears in here. So since this depends on parameter, and these parameter mu's are defined in the spaces calligraphic I1 and calligraphic I2, well, basically we need to integrate this bilinear form and this linear form in the corresponding spaces. So we end up with this bilinear form, which actually stems from the integration in both the parametric spaces and the physical space. And this is why the problem is high dimensional. And in this specific case, which is quite academic and quite simple, we are already dealing with a 5-dimensional PDE, which of course should scare us, because the question of how can we solve efficiently a high-dimensional PDE is not at all trivial. Remember that the challenge that we have in mind is efficiently computing multiple queries of the problem in order to be able to perform real-time decision-making. So we cannot think about taking one week to simulate the problem because we are working in dimension 5. And why? What this restriction means? This restriction means that traditional mesh-based approaches are computationally unaffordable, meaning we cannot think of meshing a space in dimension 5, even if we were capable of doing, which I believe this is not the case with the current technologies, but even if we were capable of meshing such a high-dimensional space, the number of degrees of freedom that we would end up with would be humongous, and so would lead to the infamous curse of dimensionality and the unfeasibility of solving this problem. And this is why what we want to do is resort to what we call a computational vademecum, which is based on a reduced order model, in order to construct an explicit parametric approximation of the problem, where the key word that I want to stress is explicit, okay? So what is the computational vademecum that I want to describe? Let's imagine it's our magic box that I'm going through the detail in a second on how to compute it, but this is our PGD vademecum, our magic box, which is a generalized solution. What does it mean? It means that it's a solution that is true for the space the space coordinate in a given interval, but also for the parametric coordinates in a given interval. And how do we compute it? We compute it following the idea of reduced order model of splitting offline and online phases using an online simulation, which can, of course, be computationally expensive, this step, but this step is performed on a fixed reference geometry, on a fixed mesh, and allows us to construct a generalized parametric solution. Generalized means that depends both on space and parameters explicitly. Once we have this, and this step can be computationally expensive, what we want to do in order to be able to perform interactive evaluation, real-time evaluations of quantities of interest, is being able to take a parameter mu, which represents, for example, a given geometric configuration or physical properties or boundary condition, put it into our magic box, and having in real time just the solution U as an output. And how do we do so? Well, our goal is to do so via a simple interpolation of the solution. And of course, this is what characterizes the PGD with respect to other reduced order models, because, for example, if you think of POD, if you're familiar with proper orthogonal decomposition, what POD does in an online step is solving a small problem with as many degrees of freedom as the number of elements in the reduced spaces. Well, in our case, with the PGD that I'm going to talk in a second, what we aim for is being able to evaluate online our solution by simply performing interpolation. And this is critical, especially in the context of industrial problems that we will see later on in the talk. So the rationale of the proper generalized decomposition goes back to the work of Akmar, Muqdad, Cinesta, and Koenigs in 2006. And the idea is approximating our solution U, which depends on space and parameters, as a rank-n separable approximation. So what does it mean, rank-n separable approximation? Is a sum of n terms, and each term over here is obtained as a product of function that depends either on space or on parameters, okay? So I will try, I'll try to be consistent with the notation throughout my presentation, and everything which is related to space is in red, everything which is related to parameter is in green, and I will try to refer to green and red also later on in the presentation. So the idea is we want to construct such an approximation which depends on function, which is a product of function that depends either on space or on parameters. How do we compute this? We compute it using a greedy approach as classical in reduced order model. So we assume that the term n-1 is known in order to compute the term nth of our expansion. So we assume that this is known in order to compute this. And in order to compute this, what we do is we project our original equation, our heat equation, for example, onto the tangential manifold, which is associated either with the direction of space or the direction of parameters. So what we end up with is an iterative algorithm, of course, in which first, in what we call spatial iteration, we assume that the parametric modes are known. So we assume that the green terms are known in order to compute the red terms, which are the function depending on space. With the newly computed function depending on space, we plug it to the green box. In the green box, we assume that the function in space is now known, and we compute the parametric modes. And we go iteratively in this way for each PGD enrichment, which means for each pair FUN in space and phi n in parameters. And we do this until a given convergent criterion is fulfilled. And this convergent criterion, generally speaking, you may think it's associated to this parameter sigma. This parameter sigma represents the amplitude of the modes. Sigma un is the amplitude of the mode n for our variable u. So, of course, it will be considered in a relative way. You can consider as a stopping criterion the nth amplitude with respect to the first one or with respect to the sum of all the previous one. But basically it tells you, it gives you an idea of the importance of the nth mode with respect to the other modes in your expansion. Okay, and in this way, the PGD construct a basis, and there are some differences with respect to traditional reduced order models that I want to stress. On the one hand, the advantages of PGD is that it does not require any a priori knowledge of the solution, meaning we do not need to sample our solution space in order to compute snapshots. We construct iteratively our basis. On the other hand, whereas traditional reduced order model a posteriori, they compute a basis which is orthogonal, what we construct here with the a priori PGD is a basis whose elements are not orthogonal by construction, which means that there may be redundant information in this construction, but this can be easily solved through a post-processing step, which is actually inexpensive, which relies on some sort of L2 projection or weighted projection in order to obtain an orthogonal basis starting from the basis that we've originally obtained for PGD. So these are the main two differences that I want to stress. And now I want to stress an important assumption that is hidden behind all this, but this is common also to other reduced order models. Actually, this goes back to the work of Tony Pattera and Gianluigi Rozza. And if you consider the second order term that comes from the integration by parts of our heat equation, so we have gradient of the test function times the matrix K, which is our conductivity, times gradient of the trial function, remember that what we want to do is separate this integral over here as a sum of terms which depends either on parameter, the green one, or on space, the red one, okay? But in order to do so, there's one critical assumption associated with data. That is, data are assumed to admit an affine decomposition. So in order to write down this integral over here as a product of green and red terms, what we need to do, we need to be able to write down the very same K matrix as a product of green terms times red terms. And this affine decomposition assumption is extremely critical, and we'll go back to it later on in this talk. But with these ingredients, we can construct our PGD vademecum. And so the first topic that I want to present to you is the construction of non-intrusive PGD-based vademecums for the specific case of viscous incompressible flows. And the keyword in here is non-intrusiveness. So this work was part of a collaboration with Volkswagen and the PhD thesis of Vasilis Tsiolakis. And the objective in this framework was to be able to utilize the infrastructure of simulation knowledge that Volkswagen has in order to devise reduced order models. What do I mean by this? I mean that industrialists are not very keen to change the way they solve problems because they have long time experience on such methods, for example, on given softwares. So our goal in here was to use the framework that Volkswagen traditionally used to solve flow problems, which is finite volume and specifically OpenFOAM, in order to devise a reduced order model. And so if we take our schematics of the alternative direction of the PGD in here, specifically in the case of non-intrusive construction, what we end up with is that the spatial iteration, so the spatial problem that we want to solve, which in this case is the incompressible Navier-Stokes that we have in here, needs to be solved how? Needs to be solved using OpenFOAM. OpenFOAM as a black box. So we want to use simple form, the simple algorithm, the simple algorithm of OpenFOAM in order to solve each one of our spatial problems. Once we've computed these spatial problems and we have our spatial modes, then we go to our parametric iteration that leads us, in this case, to a system of algebraic equations that can be solved using collocation approaches or other approaches. But the key aspect is that the non-intrusiveness of the algorithm relies on the fact that it works as a wrapper around OpenFOAM, in which at each iteration of our spatial iteration, we call the simple solver of OpenFOAM to get our solution in space, and then we iterate with our solution in parameters. Let me see some results of this simulation. This is the case of a non-leaky cavity in which we've added here at the four corners some jets. The velocity of the lead is 10 meters per second, and the jet's velocity is parameterized as a parabolic profile, and is parameterized with a peak velocity between 0.2 and 2 meters per second. Reynolds number 1000, and here I'm showing the first two modes which are associated to the boundary condition, the case of no jets, so only the velocity of the lead, and the case of maximum jets over here. And here I propose a comparison of the PGD solution with respect to the reference solution computed with OpenFOAM. Qualitatively, you can see for different values of the parameters that we are able to capture the qualitative structure of our flows and how this flow structure changes. Okay, what I want to stress at this point is that in order to compute the PGD solution for this case, the cost is basically equivalent to solving 4 to 5 full order problems within the simple. Okay, so with 4 or 5 full order solution, we are able to get a generalized solution true for any value of the parameter in this interval. And if we have a closer look, again, for the top line is PGD and the bottom line is the reference solution, what I want to stress is that the PGD is able to capture accurately the variation of the topological topology of the flow solution and the appearance and disappearance of localized vortices, okay, with no a priori adaptivity. I want this to be clear. We are not adapting in any way our space of parameters or our spatial mesh. Okay, this is all the PGD that is able through the iterative construction of the basis to capture such variations. This has been done in the context of Vasily Tsiolakis' PhD thesis, and it has been extended also to 3D, of course. And this is the case that I shown at the beginning of the HVAC. HVAC means heat ventilation, air conditioning duct. It's a part of a duct that is present in cars, and specifically in presence of this band over here, recirculation of the flow appears, and so there's a loss of optimality, of a loss of performance of these ducts. So the restriction that we had, again, were to use finite volume, specifically OpenFOAM, and being non-intrusive with respect to this method. And what we want is to study the influence of adding on this patch over here a jet that may be blowing or sucking air. Okay, and here are three values. We go from blowing to sucking. And you see that if we blow air, actually here the recirculation increases, whereas if we start to suck out air from this patch, the recirculation disappears. What we are interested in is the performance of the PGD in this context, and we obtain error which are below 2% in both velocity and pressure. But actually what we're interested in, since it's a specific industrial problem, is a quantitative of interest, which is the pressure drop. And here is the pressure drop. This is a response surface, actually, of the pressure drop as a function of the maximum jet velocity. The dashed line is the PGD, and the color solid line is the reference solution. And again, we get error below 2%. Actually, it's closer to 1% than 2%. So we are well within the standard of acceptability of industrial accuracy. Of course, everything that I presented is laminar. The following step was moving towards turbulent flows in the context of Ran's equation, and for that we relied on the experience of our partner in Volkswagen on these flows, and specifically they usually relies on models on the Spalatal-Maras turbulence model for Ran's equation for the preliminary studies on turbulent flows, and we try to mimic the structure of the algorithm that OpenFOAM does in the context of turbulent flows. Just to give you an idea what OpenFOAM does, it utilizes a staggered approach in which they compute the flow variables with a prediction, a guess of the turbulent viscosity. Then with the new value of the flow variables, they solve the Spalatal-Maras equation, they compute the new turbulent viscosity, and they go back iteratively to the flow variables. We replicated this idea here for the turbulent PGD, of course, with some variation. We used the same strategy that I described before to compute the PGD approximation of velocity and pressure using simple foam. With this pair of velocity and pressure, we computed a separated version of the Spalatal-Maras equation to compute that viscosity, and then we updated the turbulent viscosity in a separated way as well, and we went back and we go back to point number 1. Whereas the laminar Navier-Stokes case is fully non-intrusive, meaning we simply need to call simple foam, the algorithm that results from the turbulent phenomena is a bit intrusive. Actually, is what we call minimally intrusive, in the sense that we are able to use all the building blocks of OpenFOAM, the simple foam, the resolution of Spalatal-Maras, but we need to do specific calls to each one of these algorithms, and we cannot simply call the simple form algorithms and the simple form handles the turbulent viscosity equation. So we again generated a wrapper around OpenFOAM that uses the basic modules of simple form and the Spalatal-Maras and rearrange it in order for it to be able to compute a separated solution. And we tested it with the NASA wall-mounted hump, where this is a case with Reynolds almost 1 million. In the specific case, this is a section of the domain, and here we see the rear part of the hump over here. And the problem statement is such that here on this slant we added a suction jet in order to try to control the recirculation after the body. And this, the peak velocity of these jets ranges between 2 to 23 meters per second. And here we see, again, qualitatively a good agreement between PGD solution and reference solution, and how the presence of a jet, which increases in magnitude going towards the right, is responsible for reducing the recirculation, because this solid vertical line represents the position of the reattachment point in all the three configurations. Actually, if we look a bit more closely, what we can observe about the position of the reattachment point is that the relative error is always between the reduced and full order solution is always on the order of 10 minus 2, 10 minus 3. So again, we are way in the range of applicability of such method to industrial problems. So this closes up the first part of my presentation. And this part, basically, I wanted to stress you how reduced order model, and specifically the PGD, can be applied to industrial problems with the technologies that are commonly used at the moment, which are finite volume methods. Okay, but of course, if we want to look a bit towards the future as well, and specifically towards 2030, and I want to refer to the NASA report on the CF division. In this report specifically, it's a critical aspect that is identified is the necessity of using high order methods in order to perform simulations for flow problems. And this is critical because as you may be aware, high order methods are specifically attractive because they introduce low dispersion and diffusion errors. So for long time simulation, for transient phenomena, for localized phenomena like turbulent, everything which is related to diffusion tends to smear down our solution, whereas if we want to capture localized features and phenomena, we do need to preserve as much as possible the physics of the problem with our numerical scheme. So the NASA gave the scientific community this challenge to try to devise high-order methods which are feasible for industrial purposes, because it's true that high-order methods have properties in terms of accuracy, but they are at the moment less robust than existing finite volume methods, and this is why the industry is still reluctant to adopt it for simulation. But I don't want to lose too much time on this. I want to stress the fact that I'm now switching from the incompressible framework to the compressible framework. So I'm considering compressible Navier-Stokes equation right now, written in this generic form, where our unknowns are the flow variables, that is density, momentum, and energy, okay? And in the context of high-order methods, I want to start from the discontinuous Galerkin methods. I didn't put a list of references for DG because there have been many research work on these topics during the last, well, 50 years now, I would say. I want to stress the advantage of PG in terms of capability of performing local adaptivity, going high order, parallelizing, but also stabilizing convection phenomena. But of course, the main drawback of PG method, which is what limited their application to complex problems in an industrial setting, is the computational cost associated with the application of nodes, okay? And this is why a decade ago, more or less, Bernardo Cockburn, Jacob Balakrishnan, Gerard Lazarov proposed the hybridisable discontinuous Galerkin. HDG basically switched from having degrees of freedom defined for our variable u in all the nodes of all the elements, to degrees of freedom coupled only on faces of the elements, the edges in the 2D mesh that we are seeing. So the only globally coupled degrees of freedom in HDG are the U heads, which are defined on the faces. So you can straightforwardly observe that the number of degrees of freedom is much, much less than the one DG, and actually is more or less comparable with traditional continuous Galerkin of high order with static condensation. Okay, HDG is a bit more expensive, but basically not that much. Okay, so which are the advantages of HDG, and which is the rationale of HDG? First of all, it's a mixed hybrid DG formulation. Mix, it means that we are introducing some mixed variables, which are epsilon d and phi, which model respectively the deviatoric strain rate tensor and the gradient of temperature. I'm already talking about compressible flows here, okay? And then we have our U, which is the flow variable, density, momentum, and energy. And the first aspect is that the variable U, epsilon d, and phi in each element are expressed in terms of U hat. How do we do so? By performing static condensation and eliminating all the degrees of freedom inside each element and writing them as a function of the degrees of freedom on the faces. Moreover, we can use equal order interpolation, equal order approximation for all the variables. And HDG, this is a critical aspect that I will use later on in my presentation, is stable in the incompressible limit using equal order approximation. Okay, so we are devising a solver for compressible flows, but we want it to be robust also in other flow regimes like compressible ones. And of course, as I mentioned, the number of degrees of freedom is much more reduced with respect to classical DG. And of course, we have high accuracy in the sense that we can converge with order k+1, the flow variables, but also the viscous stress and the heat flux, using polynomial approximation of degree k. And this is especially useful to compute quantities of interest, which usually depends on the stresses and the heat flux rather than on the primal variables. So let me just restrict, for the sake of simplicity, to the case of Euler equation, because what I want to stress about this high fidelity simulation of compressible flows is the treatment of convection phenomena. So I will mainly focus on this convection term that appears in here from integration by parts, and specifically this F hat is what we call numerical flux. It's the information that is transfer between an element on the left and an element on the right through the interface among them. And how to properly approximate convection fluxes, this convection phenomena, has been studied by many authors. I want to mention the work by Nguyen and Pereira because it's specifically related to hybrid method, and they propose two key ingredients. The first one, expressing our numerical fluxes as a term which is related to the physical fluxes evaluated in a given state, I will be back to it in a second, plus a stabilization. And this is basically mimicking what HDG wants to do, generally speaking, with the information of the physical fluxes, okay? And specifically, the state that is chosen, which usually in compressible flows is some sort of intermediate state between the left state and the right state. Here what we do, we exploit the presence of a hybrid variable which is defined on the faces between two elements in order to evaluate this flux, okay? And then we want to encapsulate the information of the traditional Riemann solvers that have been developed by many authors along the years inside the stabilization term of HDG. Of course, in their work, Nguyen and Pereira proposed basically two Riemann solvers, one which is Lax-Friedrichs and another one which is inspired by Rho. The Lax-Friedrichs is well known to be too diffusive in order to be able to compute sharp gradients and advancement of sharp fronts, whereas Rho resolve these problems, but at the very end of the day, it may present violation of the entropy condition in presence of abrupt shocks. So our goal was trying to address this second topic without losing the accuracy of the Rho, and this is why in the PhD thesis Villa Perez, we studied HLL type Riemann solvers, which are a family of Riemann solvers which are associated with positivity preserving properties. So the idea is proposing a unified formulation like the one that was originally proposed by Nguyen and Pereira, and in which the physical flux is still evaluated using the hybrid variable, but the stabilization now assumes different expression whether we are in HLL or HLLEM. And specifically, I want to give some hints of why this to Riemann solver. The HLL Riemann solver is specifically suited for inviscid problems, so no viscosity. And they are targeting the property of positivity preserving, meaning we want to compute physical variables like densities. We want that the numerical approximation of physical quantities like density is always positive, is always physically meaningful, okay? Whereas ROE may fail to do so. Of course, there's HLLEM is an evolution of HLL. And besides the property of positivity preserving in presence of abrupt shocks, it introduces also a specific treatment of the middle characteristic, the central characteristics, which is associated with contact, and does allow also shear preservation. And shear preservation is extremely important in region of high viscosity like boundary layers. So what we expect is HLL to perform well in inviscid flows and HLL-EM to perform well both in inviscid and viscous flows. Both, they will perform well in presence of abrupt shocks. And this is why, in the context of Jordi Villa's thesis, we studied specifically various regimes, but here I want to report simply supersonic cases. This is the flow past, a supersonic inviscid flow past the NACA 0012 airfoil at Mach 1.5, so we are supersonic. We use polynomial degree 4 and the HLL Riemann solver. Of course, we are in high order. In presence of shocks, we need to do something specific for the treatment of shock capturing, and we rely on the framework of Persson and Pereire. I don't want to discuss any details about it. What I want to stress about this specific example is that this is a zoom of our domain, which of course is much larger. But what I want to stress is that our elements in the domain are extremely big, okay? And they are big because we are using high-order polynomial approximations, so we don't need a refined mesh in order to capture localized feature. And we are able to capture these from this shock that develops in here without the necessity of H refinement, just going high-order with the polynomials. This solution is computed with HLL. If we have a look at the zoom near these abrupt shocks that develops in here, the HLL solution presents a sharp discontinuity, whereas the raw solver of it here presents some weird artifacts in some elements. Actually, the color scale in these two simulations is the same, but the peak values that is achieved by HLL is around 1.8, 1.9, which is compatible with the physics of the problem, whereas in some elements, the raw solver achieves values as high as 3.5 in Mach. Of course, this is completely unphysical. These are overshoots. And if we look closely at the value of the pressure for the HLL and HLL-EM Riemann solver, they behave exactly the same, whereas the behavior for the raw Riemann solver is a bit erratic. If we don't put any entropy fix to handle the fact that rho doesn't fulfill entropy condition, we get this large oscillation that will closely lead to the conclusion of our method. If we try to put control the entropy violation, which is too small, what we end up with is a converged solution which is different from the physical one, and is the one that is representing here on the right. So this solution is converged, but it presents localized non-physical oscillations. And finally, we can retrieve a good approximation by increasing again the entropy fix delta for this method. Of course, this means that rho does not provide solution with non-physical oscillation. They can be fixed using entropy fixes, but these need to be tuned, and these are extremely problem dependent. So this method is not robust in the context of supersonic flows, whereas the HLL and HLL-EM Riemann solver are robust, and they do not need to use user-defined parameters to converge solutions. Now, let me go to another example of supersonic flow. In this case, it's the flow over a compression corner at Mach 3, Reynolds 16,000, polynomial degree k equal to 3, and of course we have again an appropriate treatment of the the shocks for high order. And the geometry is very simple, but the problem is very complex from the physical viewpoint, because we have different phenomena. We have a shock waves that develops along here. We have a shear layer near the physical wall, and here we have a region in which a compression appears. So here is a representation of the solution using k = 3, and you can observe that qualitatively we are able to get here an abrupt change of the shock. Here the velocity is, yes, this is a density field, but still, there's the shear region with the boundary layer, and here this a compression region. If we look more closely from the quantitative viewpoint, we compare the pressure coefficient and the friction coefficient with the available literature, we observe that we have a good agreement with existing results. And I want to stress that we did not do any a priori refinement in order to capture such phenomena. Of course, we have a boundary mesh, but we don't have any information related to the directionality, for example, of the shock or whatsoever. So HDG with the HLLEM Riemann solver is able to accurately represent boundary layers. This is the first aspect. It preserves the positivity in abrupt shocks and is able to handle the interaction of these two problems, which may be extremely critical. So we have a framework for high order, high fidelity compressible simulation that works fine. I'm not showing you results, but these also work, of course, for lower Mach numbers. It works for transonic flows. It works for subsonic flows. Actually, it's robust also in the incompressible limit, meaning when the Mach number tends to 0. So we can solve with HDG without any specific modification to our code, also in compressible flows. And this is what I want to talk about in the very last part of my presentation, which is about incompressible flows, and specifically about highly viscous flow. So we are talking about microfluidics, in which phenomena in which we are basically neglecting everything which is related to inertia. And I want to go back to the very first problem that I showed you, so the flow in a parameterized domain, but now in the context of highly viscous incompressible flows. So the idea of all this work is to parameterize our domain. We have a reference domain, and we can map it to any physical configuration omega mu through this calligraphic M, which is a parameterized mapping. And this parameterized mapping is expressed as a perturbation of the identity, okay? It may be analytical expression, it can be a numerical mapping. This is not really the goal of this talk. There are many different options for it. What I want to stress is our objective is to solve the Stokes equation in the domain omega mu, but we don't want to mesh any domain omega mu for any different value of the parameter, as I mentioned at the very beginning. What we want to solve is to solve in a fixed mesh with a fixed geometry omega. So the idea is to take this equation, map it back to the reference domain, and solve our equation using a high fidelity method over the reference domain. To be more precise, what we want to do is compute a generalized solution using a high fidelity method on the reference domain. So we are basically coupling the PGD framework that I introduced at the very beginning with a high fidelity HDG method that I've just presented. And our objective is to compute a solution UP, because this is a Stokes problem, which depends on the spatial coordinate capital X, which are the spatial coordinate of the reference domain, and the parameters mu, without resorting to any mesh modification, mesh distortion, remeshing, CAD modification, nothing of this kind. And of course, in order to do so, we need to write our equation from the physical domain to the reference domain through this mapping. And here enters, we go back to the original assumption of the affine decomposition of our data. We needed to find the composition of the data, which was the conductivity matrix at the beginning. And in this problem, our data is represented by the geometric mapping. So we need separability, affine decomposition of our mapping, which of course includes separability of our Jacobian matrix. This is straightforward for linearity. Let me now enter a bit more into detail on a specific problem that arises when we use continuous Galerkin methods, okay? And observe this term here. This term here is the term that comes from the discretization of the second order term in our Poisson equation. So it's the gradient of the test function contracted with nu, which is the viscosity, the gradient of the trial function. This is similar to what we've seen at the beginning with the conductivity matrix, but now this is defined over the domain omega mu, which is the physical domain. And what we want to do is map everything back to the reference domain omega. And so I'll skip the details, but basically this comes from the traditional mapping in continuous mechanics. When we map from a physical configuration to a reference configuration, the inverse of the Jacobian matrix appears, and also the determinant appear over here. And so what we end up with is this expression in which we have the gradient on the reference domain contracted of the test function contracted with a gradient on the reference domain of the trial function, our unknown, but also a matrix H over here. And this matrix H is defined over here, and it features the inverse of the determinant. The inverse of the determinant is not separable analytically. It can be separated in a numerical fashion using, for example, high-order PGD projection. This was which was originally proposed by David Modesto, Sergio Zlotnik, and Antonio Huerta. And in these recent papers by Sevilla, Zlotnik, and Huerta, they show that this matrix H is actually may actually represent a bottleneck because they need to be separated numerically. So what we try to do is try to work around this issue, and specifically this was done in the context of Luca Borchini's thesis. And the idea was as simple as rewriting the second-order PDE system as a first-order PDEs. How to do so? Well, exploiting the HDG framework and using the mixed variable. The mixed variable, remember, at the beginning I presented the heat flux and the strain rate tensor, which are first-order derivatives of our primal quantities. And in this specific case of Stokes equation, we consider the gradient of the velocity. So if you do so, the very same term that before was a second-order term is now expressed, the viscous term, as a first-order term with a divergence of our mixed variable in the physical domain again. When we map it back to the reference domain, of course, the inverse of the Jacobian and the determinant appear, but there's only one function that is differentiated in this context. And so what we end up with is a matrix A, and this matrix A is the adjoint of the Jacobian. And in a recent work, very same work by Sevilla, Zlotnik, and Huerta, they show that this matrix adjoint of the Jacobian is separable analytically, and of course with a finite number of modes, which depends on the mode of the mapping. But that I don't want to enter into too many details. So we have a framework here that allows us to separate analytically our equation. And so let's see how it works in the context of geometric vademecum. This is an example of a flow past a parameterized sphere. So we parameterize the radius and we solve in an axisymmetric framework. And since it's a Stokes problem and we have an analytical solution, what we can compute is the accuracy of the reduced order models. And we do so by comparing the order of convergence for velocity, pressure, and gradient of velocity. Remember that since we're using HDG, the gradient of velocity is a variable itself. It's not computed as a post-process of the velocity. And we observe that we have optimal convergence of degree k+1 in the high-dimensional space omega times calligraphic I. So this is the high-dimensional space of our solution, which accounts for both spatial and parametric directions. So we have optimal convergence for all the variables. The method is LBB compliant, so it's stable in the compressible limit. And since all the modes that we are computing are stable, and then we are just constructing a combination of such modes, we don't need any pressure supremizer or additional stabilization, like, for example, POD method may require. And finally, exploiting the properties of HTG, we can construct a local online post-process, which leads us to a velocity which converges with degree k+2. So we may get extra accuracy in the velocity as well. Let me show you an example of a physical problem of interest in microfluidics, which is the push-me-pull-you microswimmer. This is basically a device that was studied by several authors, including or starting from the work of Hebron and co-workers. There are two spherical bladders over here that may exchange mass. The global mass of this device or this organism is constant, and they may also change their distance. So this is the computational mesh that we employ with polynomial of degree 4. You see that the mesh is rather coarse, and we have two parameters that describe our domain. A parameter mu, which is associated with the inverse of the distance between the two bladders, and the parameter mu2, which is associated with the radius of the first bladder, knowing that the global mass is constant. And this, again, is solved in an axisymmetric framework. And let me see if the video works. Yes. Here we have an animation of after computing our computational vademecum using PGD, how changing using the sliders over here, the mass distribution and the distance between the two bladders, how online we get the realization of the different geometric configuration with the streamlines. And what we see here on the bottom is what we call a response surface, actually separated response surfaces, because we've constructed, starting from our PGD approximation, a response surface of the drag force of the two spheres as a function of the two parameters. And we will see in a second, yes, here, how changing different parameters here or devising here different trajectories within the space of the parameters, we are able to evaluate in real time our drag. This computation is real time in the sense that it's the simple evaluation of the vademecum that we constructed before. So the vademecum allows us to construct parametric solution and separated response surfaces. Now, the final topic that I want to address now, and I think I'm running short of time, yes, is this method competitive from a computational viewpoint? And how does it compare with respect to traditional a posteriori sampling-based approaches? Well, posteriori PGD, compared with the posteriori PGD, which is a version of the PGD which relies on snapshots, okay? So the cost of the a posteriori PGD is basically the number of snapshots, and the cost of the a priori PGD is the number of computed modes times 1 plus the number of iterations that we perform in the alternating direction loop that I presented at the beginning. And here is exactly the same case of the two bladders that I've presented before. What we are interested in is a target accuracy of the drag of 10⁻3. We compute with the a priori PGD 500 modes. Actually, this is a bit overkill. We need less, but let's take 500 as a round number. 500 modes with 2 iterations means that we need to solve 1,500 spatial problems. To achieve the same accuracy here, the PGD solution requires 16,000 solutions, okay? So basically, we have 11 times less spatial problems to be solved using the a priori PGD in order to get the same accuracy in the quantity of interest as the a posteriori PGD. So this method looks competitive, and let me just finish commenting that, of course, the geometry that we study is rather idealized. In a recent work, we studied different configuration. This is just full order solution of complex microswimmers. Of course, we would like now to study this kind of configurations also in a parametric way. So can we move from one configuration to the other using mappings? This is something that we would like to address. And this leads me a bit to the summary of what I presented today. I presented basically two topics, one related to the proper generalized decomposition, which offers a versatile framework for the construction of computational vademecums, meaning the possibility to compute fast multiple queries of parametric problems, to construct separated response surfaces of quantities of interest, and then perform real-time interactive studies like flow control or parameterized geometries. And these, of course, can be done using in-house codes, but also non-intrusive implementation, which are especially critical for industrial applications. Concerning a bit more towards the future of the solvers, I've been talking about the hybridisable discontinuous Galerkin method, which in my opinion represents a robust framework for the challenge of industrializing high-order methods for flow problems, because it provides highly accurate spatial discretization with optimal convergence of stresses and heat fluxes, with a reduced number of degrees of freedom with respect to traditional discontinuous Galerkin, a natural way to stabilize convection, and to propose stabilization which is positivity preserving, like the HLL families that we've presented before in a hybrid framework. And of course, since it's accurate in the solution, it will be accurate also in the computation of quantities of interest. So where does leave us with some ongoing work that I want to mention that is going on between UPC and SIMNE, or in both. Alejandro Piñero in his thesis is working on high fidelity HDG solver for unsteady problems. Everything that I presented up to now was steady. Davide Cortelesa and Luis Vieira, they're working on the last topic that I mentioned, so the robust finite volume solvers for problems either in microfluidics or in viscous flows at higher Reynolds number. And in the context of the Severo Ochoa SIMNE, the Álvaro Borrás, Rafael Pereiro recently started the thesis, and they're working more on the computational vademecums, PGD vademecums, with different kind of applications in mind, from microfluidics to external hydrodynamics. I couldn't find a photo of Rafael, so I just put a curly emoji. Please, Rafael, forgive me. Thank you, everybody. And if you have any question, of course, I will be more than glad to hear you.
Thank you very much, Matteo. It was really good, your presentation, very impressive. We are very short time, but if somebody wants to ask a question, please open the mic or write in the chat. Okay, if there are no questions, then let's finish the seminar like this. Thank you again, Matteo, for this work and this nice presentation. And I hope to see you all in the next session of the SIMNE seminar course. Thank you, everybody.
Thank you, Ignacio. Thank you, everybody.
Bye-bye.